Welcome to the deep dive. Today, we're tackling something called granular computing.
Mm-hmm.
Think about it as a way to, get a handle on information overload. It's about dealing with data in meaningful chunks.
Yeah, clumps, really. The field called them information granules.
Right, granules. And we're mainly drawing from Mohammed Medhagabar's introduction to the topic.
Our goal really is to explore how grouping data like this actually helps simplify, well, really complex problems.
Especially when things are uncertain.
Exactly, when there's uncertainty involved.
Yeah.
Instead of getting lost in every single data point, granular computing lets us operate on these aggregated clumps, these granules.
Yeah, exactly. Like, imagine trying to understand a really busy city.
Okay.
You could try to track every single person, every single car.
Which would just be chaos.
So,
impossible.
Total chaos. Or you could look at neighborhoods, traffic flows.
Yeah.
Those are kind of your granules in action,
Well,
right?
that's a great analogy, yeah.
So for you listening, have you ever felt just swamped by data? Like you can't see the forest for the trees? Well, that's basically the core problem granular computing tries to address. It offers a way to, cut through the noise and find meaningful patterns.
Okay, so maybe let's start with the basics then. What exactly is an information granule?
Good question.
Essentially, it's a collection of data points, things that are bundled together based on some kind of unifying characteristic.
Like what? What kind of characteristic?
Well, it could be their similarity. Think of all the apples of a certain type together.
Okay.
Or maybe their indistinguishability, like sensor readings that are all within a certain margin of error. You can't really tell them apart precisely.
Right, too close to call.
Yeah, or just proximity houses in the same neighborhood, perhaps.
Got it.
Or even their function. Think about cells in your body working together on a specific job. That group could be a functional granule.
So, okay, instead of focusing on one specific apple, we're looking at a group of, say, Granny Smiths. Makes sense.
Exactly.
And what's the fundamental idea behind actually working with these granules? Why do it?
The core principle is actually pretty straightforward. You take a complex problem, a big whole, and you break it down into smaller, more manageable parts, the granules.
Okay.
Then you process those parts, those granules, and then you combine the results somehow to tackle the original, larger problem.
So it's a bit like divide and conquer.
Very much like that, yeah.
No.
But applied directly to the data itself, structuring the data that way.
So it's also about representing knowledge at different levels, like zooming in and out.
Precisely. Different levels of abstraction. Sometimes you need that high-level overview, the big picture. Other times, you really need to drill down into the details. Granular computing gives you the flexibility to switch between these levels.
And how does that help specifically? What are the benefits?
Well, a key advantage is how working with granules helps us manage things that are really common in real-world data. Things like uncertainty, incomplete information, maybe just inherent imprecision.
I see. So if you've got a blurry photo that's incomplete data, right? Analyzing groups of pixels, the granules, might help you figure out what the picture is of, even if the fine details are lost.
That's a good way to put it. And it feels quite natural, doesn't it? It feels like how our own brains work.
Yeah, I was just thinking that. It sounds very intuitive.
Absolutely. That connection to human cognition is really quite insightful.
Yeah.
Our minds constantly categorize information, chunk it together to make it easier to process.
Like learning a new language. You learn words, then phrases, then sentences.
Exactly. They start with basic steps, group them into routines, combine those routines. That's granulation right there. We also use hierarchies all the time, like classifying animals, kingdom, phylum, class.
Right. Different levels of detail.
Different levels.
Yeah.
And the level we actually focus on often depends entirely on the context, on what we're trying to do.
Makes sense. If you're just, walking into a party, you might just notice loud music, lots of people, very coarse. But if you're trying to actually hear someone specific, you tune into their voice, ignore the rest, much finer detail.
Precisely. So that level of detail, or granularity, is absolutely crucial here.
Okay, so let's pin that down. What does granularity mean in this specific context?
Granularity, yeah. It basically refers to the scale or the level of detail at which we're analyzing or processing our data. It's a spectrum.
A spectrum.
Yeah, ranging from very fine, where you're looking at every single individual data point, all the way to very coarse, where you're dealing with these large clumps, these big granules.
And there's always that trade-off, isn't there? More detail means more precision, probably.
Usually, yeah.
But it takes more computing power, more time. Less detail is faster, maybe, but you might miss something important.
That's the fundamental trade-off.
Exactly.
And this is really where granular computing shines. It aims to let you operate at the most appropriate level of granularity for whatever task you're doing. Not too fine, not too coarse, just right.
Okay, and that brings benefits.
Oh, definitely. Some significant benefits. First off, it simplifies complex problems.
Yeah.
Massively. Well, problems that would be, frankly, computationally intractable. Just too complex to solve at a very fine level of detail. They can become manageable when you step back and work with granules.
Can you give an example?
Sure. Imagine trying to find subtle trends in billions of individual website clicks happening every second.
Oof. Yeah, that sounds hard.
Right. But identifying broader patterns in overall user behavior, maybe grouped by demographics or time of day that's much more feasible, you're working with granules of behavior.
That makes perfect sense. Okay, simplification. What else?
It also enhances how we interpret the data. We touched on this because it aligns better with how we humans naturally reason. We think in concepts, categories, granules.
Right, it feels more intuitive.
It does. And then there's computational efficiency. Pretty obviously, working with coarser granules just requires less processing power, less memory, less time.
Which is always good.
Always good.
Yeah.
And importantly, these granular representations can actually be more robust, more resilient to uncertainty and noise in the raw data.
How does that work?
Because those little individual fluctuations, the noise, they tend to get averaged out or smoothed over within the larger granule. The granule represents the general trend, not every tiny blip.
Okay, interesting. And can the system, change its level of detail on the fly? Can it adjust the granularity?
Yes, absolutely. This dynamic adjustment of granularity is a key strength in many granular computing systems.
So it can adapt.
You can adapt. A system might optimize its performance by focusing its resources, its computational effort, on the levels of detail that are most relevant at that moment.
Like starting broad and then zooming in.
Exactly that. Yeah. It might start with a broad, coarse-grained analysis to get the lay of the land, identify key areas of interest, and then zoom in with finer granularity for a more detailed look just where it's needed.
Pretty smart. Okay, so these ideas, they feel like they might have been bubbling under the surface for a while. What are the historical roots here? Where did granular computing actually come from?
That's a good point. Understanding the history often helps. The real groundwork was laid back in the mid-20th century, even before the term existed.
Oh, really? Like what?
Well, Lotfi-Zaida's fuzzy set theory back in 1965. That was absolutely crucial.
Fuzzy sets.
It gave us a mathematical way to handle data that wasn't just strictly true or false, black or white. It allowed for degrees of truth, degrees of belonging.
Shades of gray.
Exactly, shades of gray. It was a new way to represent these information granules, capturing that idea of partial membership. So, something could be considered somewhat hot or mostly tall, not just hot or not hot. It broke away from traditional binary logic.
Interesting. So allowing for that fuzziness, what came next?
Then, in the 1980s, Zitscha Pollack introduced rough set theory.
Rough sets. Okay, different name, different idea.
Similar goal, different angle. Rough sets were designed to deal with vagueness and ambiguity, but they did it by approximating precise sets using a lower and an upper boundary.
Lower and upper boundary.
Yeah, based on the information you actually have. So instead of degrees of membership like fuzzy sets, rough sets focused on. Based on my available data and my ability to tell things apart, does this element definitely belong to the set? That's the lower approximation. Does it possibly belong? The upper approximation? Or does it definitely not belong?
Okay, so it's more about the certainty of classification based on the available evidence.
Exactly. The key idea was information discernibility. What can we actually distinguish?
So let me see if I've got this. Fuzzy sets are about the degree to which something belongs, like 70% hot.
Right.
And rough sets are about the certainty of belonging based on whether we can distinguish it definitely in, possibly in, definitely out.
That's a really good way to summarize the distinction. Yeah.
Okay, helpful.
And these two theories, fuzzy sets and rough sets, they were really pivotal. They highlighted how important it is to think about granularity, about how we represent and process information.
And then the term granular computing itself appeared.
Yeah, that gained traction more in the late 90s, early 2000s. Zaida himself and other researchers started to realize the power of bringing these different approaches, fuzzy, rough, and others together under one umbrella. integrating them into a cohesive field.
And it's kept evolving since then, I imagine.
Oh, absolutely.
Yeah.
It's been increasingly integrated with, all the big areas, machine learning, data mining, AI. This has led to more powerful algorithms, things like granular neural networks.
Okay.
New theoretical frameworks have also emerged.
Yeah.
We now talk about things like evidence theory, interval analysis. They add more tools to the granular toolkit.
Right.
And we're seeing more sophisticated models that use multiple levels of granularity hierarchies to tackle really complex systems. Plus, there's that growing interest in the connections to cognitive science. How does this relate to how we think?
Fascinating. Okay, so now we have a feel for what it is, where it came from. What are the fundamental types of these information granules that we actually work with? You mentioned fuzzy and rough sets.
Right, those are two major ones. But there are others. Each has its own way of handling uncertainty and imprecision.
Let's recap fuzzy sets quickly then.
Okay, fuzzy sets. Partial membership, degrees from 0 to 1. Really good for modeling vague linguistic terms like tall, warm, fast. Uses fuzzy logic operations.
Got it. And rough sets.
Rough sets.
Yeah.
Uncertainty comes from indiscernibility, inability to distinguish based on attributes. Defines that lower approximation definitely belongs, upper approximation possibly belongs, and the boundary region, the uncertain bit in between.
Okay.
What are those interval mathematics? This is maybe simpler conceptually. Numerical quantities are represented not as single points, but as intervals, ranges, like the temperature somewhere between 20 and 22 degrees.
So A-B, a range.
Exactly. A, B. Very useful when dealing with measurements that have known error margins or bounds. You perform arithmetic directly on these intervals.
Right. Handling and measurement uncertainty.
Precisely. And finally, probabilistic granules. Here, uncertainty is represented using probability distributions.
Like a bell curve.
Could be a bell curve, could be another distribution. It gives you a range of possible values, but also tells you the likelihood of each value, or ranges of values, occurring. You use statistical measures like expected value, variance, Bayesian methods.
Okay, so let me try to map these onto something. Maybe customer analysis.
Go for it.
Fuzzy sets could model customer satisfaction, like mostly satisfied.
Yep.
Rough sets could help classify customers based on incomplete survey data. Definitely a potential buyer. Possibly a potential buyer.
A good example.
Interval math could represent their age range if we don't know the exact age, like between 30 and 40.
Makes sense.
And probabilistic granules could estimate the probability they'll purchase a certain product in the next month.
Those are all excellent illustrations of how the different types capture different facets of uncertainty or granularity.
Cool. Okay, so those are the types of granules, but how do we actually make them? How do we get from raw data points to these useful clumps? What are the main methods for granulation?
Right. The practical side. How do we actually form the granules? This is where algorithms come in.
Figured.
There are quite a few techniques, and which one you choose really depends on the data you have and the problem you're trying to solve. Clustering algorithms are a huge category here.
Clustering, like grouping similar things.
Exactly. Probably the most famous is k-means.
Heard of that one?
Yeah, you basically tell it how many clusters K you want to find, and the algorithm tries to partition the data so points in the same cluster are close to the cluster's center, or mean.
Okay. Simple enough, conceptually.
It is, though it can be sensitive to where you started off. Then there's hierarchical clustering.
Hierarchical.
Yeah, this builds a whole hierarchy, a tree structure of clusters. It can work bottom up, starting with each point as its own cluster and merging the closest one step by step. That's called agglomerative.
Merging up.
Or it can work top down, starting with all data in one big cluster and progressively splitting it. That's divisive. You often visualize this with a dendrogram, that tree diagram.
Ah, I've seen those. Lets you choose the level of clustering later.
Exactly. And then there's fuzzy c-means. Remember, fuzzy sets.
Partial membership.
Right. Fuzzy c-means is like k-means, but it allows data points to belong to multiple clusters at the same time with different degrees of membership. Really useful when your data doesn't have hard boundaries, when things overlap.
Okay, so k-means forces a hard choice, hierarchical gives you levels, and fuzzy c-means allows for ambiguity.
That's a good summary. Another really important method, especially related to rough sets, involves equivalence relations and partitioning.
Equivalence relations. Sounds mathematical.
It is, but the idea is simple. You define a rule. When are two data points considered indistinguishable based on the attributes you care about?
Like, two customers are indistinguishable if they live in the same city and are in the same age bracket.
Perfect example. That rule, that indiscernibility relation, naturally divides or partitions your entire dataset into distinct groups or equivalence classes.
Mm.
Every item in a class is indistinguishable from the others in that class, according to your rule.
And those classes are the granules.
Exactly. That's fundamental to how rough sets work.
Okay, what else?
We also have simpler methods, like quantization. This is often used for numerical data. Think about dividing a continuous range, like income, into discrete bins or intervals.
Like low, medium, high income brackets.
Precisely. You could do equal width binning, where each bin covers the same range, like 0, 20K, 20K, 40K, etc. Simple, but might not reflect how the data is actually distributed.
Right, you might get empty bins or overcrowded ones.
Or you could do equal frequency binning, where you try to put roughly the same number of data points into each bin.
Yeah,
This adapts better to skewed data.
got it. Binning. Simple but effective sometimes.
Definitely. And finally, let's not forget we can use human expertise, expert knowledge.
Bringing the humans back in.
Absolutely. You can have rule-based granulation, where domain experts define the rules for what constitutes a granule. If temperature is above X and the humidity is below Y, then it's in the comfortable granule.
Based on experience.
Exactly. Or you can use more formal structures, like ontologies, structured representations of knowledge in a domain, to guide the formation of granules. This can make the granules much more meaningful and interpretable.
Okay, so just recapping those methods. Clustering finds natural groups. K means hierarchical, fuzzy. Equivalence relations partition based on indistinguishability, like in rough sets. Quantization bins numerical data, equal width, equal frequency. And expert knowledge defines granules directly. Rules, ontologies.
You've got it. A whole toolkit for creating granules.
That really clarifies how we get from just, a pile of data to these structured, usable granules. Okay, so where does this actually make a difference? Where do we see granular computing being applied in the real world?
The applications. Yeah, it's surprisingly broad, actually. A really key area is data mining and knowledge discovery.
Okay, how?
Think about market basket analysis, figuring out what products people buy together.
Right, the classic diapers and beer example.
Exactly. But instead of just looking at individual products, granular computing lets us find relationships between categories or types of products.
Yeah.
Granular association rules.
So not just brand X coffee and brand Y creamer.
Right. But maybe something more general, like customers who buy breakfast items are highly likely to also purchase beverages. You're working at the granule level of breakfast items and beverages.
That sounds much more strategic for store layout or promotions.
It absolutely is. It gives you a higher level view. It also plays a pretty big role in machine learning.
How so?
Well, people have developed things like granular neural networks or granular support vector machines. The idea is that incorporating granularity can improve the learning process, make the models generalize better to new data, maybe make them more robust.
Interesting. What else?
Decision support systems often use granular models. When you have complex decisions with lots of criteria, maybe uncertain information, representing options or criteria as granules can help structure the problem.
Makes sense for complex choices.
Yeah. And then there are more specific domains. Bioinformatics is a big one.
With all that gene data.
Exactly. Huge amounts of data, often noisy, very high dimensional. Granular computing provides tools to manage that complexity, find meaningful patterns in gene expression, maybe identify disease markers without getting lost in the weeds.
Cutting through the genetic noise?
Sort of, yeah. Image processing is another area. Instead of analyzing images pixel by pixel, which can be slow and sensitive to noise,
Right.
granular approaches work with regions or segments of the image as granules. This can make tasks like image segmentation, finding objects, or pattern recognition much more efficient and robust.
Analyzing chunks of the image instead of dots.
You got it. And even in things like social network analysis.
Like Facebook or Twitter data?
Yeah. Granular computing can be used for community detection, finding groups of users who interact a lot, or understanding how information or influence spreads through these groups, where the groups themselves are treated as granules.
Wow, okay. So it really pops up in a lot of places where there's complexity, uncertainty, or just massive amounts of data.
That's the common thread, yes.
Yeah.
Wherever dealing with the finest level of detail is either impossible or just not the most insightful way to go.
Right. So as we kind of wrap up this deep dive, what's the main takeaway? The key message about granular computing we should leave with?
I think the fundamental takeaway is that granular computing offers a really powerful and arguably quite natural lens for viewing and processing information, especially given the just ever-increasing complexity of data in our world.
It's a way to cope.
It is. By abstracting away from the nitty-gritty details and focusing on these meaningful clumps, these granules, it mirrors a really fundamental aspect of how we as humans make sense of everything around us.
Yeah, it's about finding that right level of focus, isn't it? The right granularity to see the important patterns without getting totally bogged down. So maybe a final thought for you, the listener. Think about the information you encounter every day. Is it overwhelming sometimes? Are there ways you could perhaps mentally group or abstract that information? Find the granules in your daily data stream.
Interesting challenge.
Could doing that help you gain clearer insights, maybe feel a bit less swamped? This deep dive, it's really only scratched the surface of this field.
Oh, definitely.
There's a whole universe of specific models, algorithms, and as we heard, real-world applications out there still waiting to be explored.
A fascinating area.
Indeed. Well, thanks for joining us for this exploration of granular computing.